Sajid. We have lecture 7, that is unit commitment method, and the presentation will be given by Asim, Umayya, and Asad. So the main focus of my presentation will be on these topics, on unit commitment basic introduction, dynamic programming, that is method of unit commitment, and its type forward dynamic programming, and one of its example, and at the end I'll show you one short video on it. So can you see my slide and this PPT?
Yes, we can see and hear you.
Okay, thank you so much. So let's have some review on what is unit commitment, then we will move here on its methods. Unit commitment is an optimization process where the system operators choose the production unit state on, off, and their production level in order to minimize the production cost, system price, or social welfare, and to meet demand, though a period of time, a day, ahead, or week, subject to stop, ramp rates. So mainly we have to keep in mind one thing, that we have to choose the cheapest unit for our purpose. You can view unit commitment in a sequence dispatchment. Unit commitment is an operation planning. The purpose of planning is to determine a schedule called unit commitment schedule, which tells us before when which unit to start and shut down during operation over the specified time, such that the total operation cost for the period becomes minimum. Unlike economic load dispatchment, the objective of planning is not to distribute the load in time between the units already running, such a manner that every instant varying operation cost becomes minimum. So main focus of unit commitment. Unit commitment is an optimization process and to determine operation schedule. Let's come to our topic, that is method of unit commitment. So the advantage of this dynamic programming is it is reduction in dimensionally of the problem. So how we will say that we will maximize the combination. Suppose we have found units in a system and any combination of them could serve single load. There would be a maximum, like any the general formula of this is 2 power n minus 1. That will be the total combination of our units. Like Salman said in previous slides in his lecture, that one load can be optimized for all given demand. Well, in my opinion, it is not mandatory that one plant should be sufficient, because if that plant will be shut down, the whole system will be affected. So we have to keep in mind at least 2 plants at the same time. So we will be on minimum demand. However, if a strict priority method is imposed, there are different combinations. If we have 4 units, so we have to use that in that series. The imposition of priority list arranged in order to full load average cost rate would result theoretically correct dispatchment. So these are mentioned here. The no load costs are 0, unit input output characteristics are linear, there are no other limits, constraint, and restriction, startup cost or fixed amount. So in dynamic programming approaches that follow, we assume a state consists of array units which specify unit operation and the rest offline. The startup cost of unit independent of the time it has been off. There are no cost of shutting down a unit. There is a strict priority order, and in each interval a specified minimum amount of capacity must be operating. So let's talk about this forward dynamic programming approach. One could set up dynamic programming algorithm to run backward in time starting from the final hour to be studied. Back to initial hour. Conversely, one could set up the algorithm to run forward in time from the initial hour to the final hour. The forward approach has distinct advantage in solving generated unit commitment. For example, if the startup cost of a unit function of the time it has been offline or by any restriction like temperature, then a forward dynamic programming approach to its minimum suitable, since the previous history of the unit can be computed at each stage. There are other practical reasons for going forward. The initial conditions are easy specified and consumption forward time as long as required. So we have to mainly focus on this, our general formula, that is algorithm compute minimum cost in our K with combination I. So this is our given general formula, fuel cost and these all. So let's come our problem that is given in this figure. Consider a system with 4 units to serve 8-hour load pattern. So we have 4 units and total 8 hours. Table for unit characteristics, load pattern and initial step for the cases in given example. In general, 4 units which have used to solve 8 hours load pattern and load demand is here in megawatt that you can see. So if we select starting 4 units like this, that will be unit 1, unit 2, unit 3 and unit 4, and its cost is written here. So case 1 is strict priority listing method that we have to select from this table. As we know that we have learned in previous our subjects that 0 is showing on and 1 is showing, or 0 is showing off and 1 is showing on. So there are different capacity that we have to follow to achieve maximum demand that is required by our system. So P cost, that is we have to select first and 15th, and by general formula we can get this result. F cost, fuel cost, that will be given by general formula. We have to put those values and we will get this result. Similarly, for hour 2, we have to follow all our previous results to meet on this 530 megawatt. So for 530, we have to select 12, 14 and 15. By our general formula, we have to calculate these values. So let's see a short video that is related to our industry.
In this transmission model example,
can you hear voice of this video?
Yes.
Yes.
current and dispatch optimization module is demonstrated. Study case and scenario 08 unit commitment should be activated. The unit commitment and dispatch optimization simulation minimizes the operating costs of the system over a defined period of time. It allows market data to be integrated into the network model and used for optimizing the generation dispatch. The calculation combines the optimal power flow calculation algorithm with quasi-dynamic simulation and is accessed via the optimal power flow unit commitment toolbar. The optimization can be based on either an AC or DC load flow, and in this example, will be run as an AC-based optimization at hourly steps over a period of 5 days. On this page, the objective function is selected. The default is to minimize total costs, but the user can instead select individual cost components to be minimized. In this project, characteristics are assigned to the active power of loads and generating units, and the generators also have cost data assigned, which is required for the unit commitment calculation. Let us look at the unit commitment data of generating units. The unit commitment page is the same for synchronous machines and static generators. But if a unit is defined as a variable renewable energy source, or VRE, we can only enter costs for curtailment, as it is assumed that the unit is not normally dispatched. In this example, all static generators are flagged as the REs. We edit the synchronous machine, where the active power is selected as a control variable for the unit commitment. We can see the operational limits and have selected them so that they will be observed during the calculation. On the Operating Costs tab, we can specify the operating costs locally or via separately defined cost curves. In this project, generic cost curves for each fuel type have been used. They are stored in the operational library. In the generated cost curve, the resulting costs are calculated based on the individual cost components, like fuel costs and efficiency. The emission costs have an absolute characteristic assigned. On day 126, the fourth day of the simulation period, the value of the emission costs is changed from $15 per ton to $50 per ton. This is used to illustrate heavily increased CO2 emission costs that could occur in the future. As the emission intensity is higher for coal than for gas, emission costs are more onerous for coal, and so we expect this to be reflected in the redispatch of the two fuel types. Additional redispatch costs can be defined, as well as startup and shutdown costs, and ramp rates and minimum on and off times may be entered here. Returning to the command dialog. On this page, the controls and constraints are defined. We will just use active power dispatch as a control, and we are considering the active power limits as constraints. A control or a constrained variable is only considered in the optimization if it is selected in the network element, and the class of control is selected in the unit commitment and dispatch optimization command. In this example, we are considering branch flow constraints which are set to a loading value of 100% for lines and transformers, and voltage constraints for main bus bars with a range between 0.95 and 1.05 per unit. Also for the southwestern part of the network, a boundary constraint is defined and observed. The boundary flow constraint limits the active power flow to plus/minus 400 megawatts. There is an option to consider planned outages on the network. In this case, there are several planned outages during the simulation period, but the one which is relevant here is an outage for 3 hours on a generated transformer at one of the nuclear power plants. This will force the unit commitment to ramp down the generation from this power plant and observe the specified downtime of the generator before it goes back online. The results for all control and constrained variables can be recorded automatically and are stored in a before optimization and after optimization result file. The before optimization results are essentially the results of a quasi-dynamic simulation which are used to initialize the unit commitment. A summary result file is also written. On the algorithm page, the user can select one of the two inbuilt solvers, but there is also the possibility to make use of an external linear programming solver to make the calculation much faster. We will use the recommended default CPC solver. The rolling horizon functionality is enabled. This will split up the minimization problem into several smaller subproblems and will therefore result in a faster and more stable simulation behavior of the solver. We will now execute the unit commitment simulation. In order to execute the unit commitment and dispatch optimization in Power Factory, it is necessary to have a converging load flow in every time step of a quasi-dynamic simulation in a defined time period, because the load flow results of each time step are used for the initialization and linearization of the mixed linear integer problem that is solved in the unit commitment. After execution, There are several ways to view and investigate the results. Statistical results can be viewed in a flexible data page, or on a graphic, and result quantities across the time period are also available and can be visualized using plots. These plots show the active power dispatch summed up for the different fuel types. The two plots show the generation as it would be using a simple quasi-dynamic simulation, and then as it is, after the redispatch by the unit commitment optimization. We see that the nuclear generation is now at its maximum, and we can see the effect of the increased emission cost after day 3. The generation from coal is reduced for day 4 and 5 of the simulation and substituted by an increase of the gas-fired power plants. This effect can also be observed in this redispatch plot, and the effect of the planned outage of the transformer at the nuclear power plant can be seen. The missing feed is compensated by coal power plants. When we look at the outage in detail, we can see that the ramps and minimum downtime are only considered in the unit commitment and dispatch optimization and not in a simple quasi-dynamic simulation. The downtime is extended by 2 hours to meet the required 5-hour downtime for the power plant. This plot shows the interchange of the southwestern part of the network with the rest of the system. We have defined a soft constraint of between minus and plus 400 megawatts for the interchange, and we can see how this constraint is respected. Inbuilt reports are also available, such as this optimal solution report. Here we can see, for example, redispatched energy and costs for generators. We can also use diagram coloring to see immediately whereabouts in the network the redispatch energy or redispatch costs are incurred. These are the costs associated with the generation changes, compared with the default quasi-dynamic simulation, which have been made in order to minimize overall costs. This button allows you to load the time sweep results from a result file to investigate the individual time steps in a single line diagram or the network model manager.
So this was the presentation. As I have solved this example, that will take more than 1 hour to me for solving this problem, so I didn't solve on whiteboard. Another thing is that if I will solve, that will take more time. So if anyone have question, he may ask.
Okay, no question, maybe.
Okay, Loshi. So I will call Mr. Mohammad Asim for next slide from 13 to 18.
Okay.
Okay, thank you.
Thank you.
Asim, continue.
Okay. See the screen, sir?
Yeah, we can see.
Okay, thank you so much. So, unit commitment solution by Lagrange relaxation. What is first we will discuss what is Lagrange relaxation and why we use it for unit commitment. So Lagrangian relaxation is a method for approximating a difficult problem of constraint optimization by a simpler problem. So for that reason, we use Lagrange relaxation because unit commitment require a very secure method to optimize the constraint optimization. So and why we use Lagrange relaxation method? Why? What is the need of this method? Because the dynamic programming method of solution of the unit commitment problem has many disadvantages for large power system with many generating units. So for the better optimization, we use Lagrange relaxation method. Here, consider the classical constraint optimization problem. These two are the constraint optimization problem. One is primal problem, minimize f of x1 up to xn subject to omega x1 up to xn is equal to 0, and the Lagrangian function. We will discuss further the Lagrangian function and will solve an example on Lagrangian function, and the Lagrangian function is Lx1 up to xn is equal to f of x1 and up to xn plus lambda omega x1 up to xn. This is the Lagrangian function. So first we will solve an example. Okay, this is the example, and I will. Can you see the whiteboard, sir?
Yes. Yes.
Yeah,
it's
Tim,
okay.
we can see.
Okay. So to solve this problem, we already discussed the Lagrangian function. So for dual function, we will write the above value in Lagrangian function equation, and the Lagrangian function equation we already discussed. That is Lx1. How to write x up to xn. कैसे लिखूं यार?
Okay, Asim, you can just say the values of bi-verbally.
Okay, to find the Lagrangian function and to solve this example, first we will take partial derivative of x1, that is x1, x2, and first we will write this equation in Lagrangian function, and after that we will take a partial derivative of x1, x2, and lambda, and we will get the following value. Let me write. After taking the partial derivative, we will get these value. X1 is equal to 0.5. X1 minus lambda for x2 to x2 minus lambda, and for the function lambda, if we take derivative with partial derivative with respect to lambda, we will get 5 minus x1 minus x2. So to find the value for lambda, we will equate this equation. So we will get x1 is equal to lambda by 0.5 and for f of x2 is equal to lambda by 2, and for lambda minus x1 minus x2 and minus 5. Now putting the values of minus lambda by 0.5 and for x2 lambda by 2, and in the f of lambda equation. So we will get lambda is equal to 2. So the value of lambda is equal to 2, and from this value we can get different values by putting it into the equation, from which we can conclude the minimize or maximize function. Now, iterative form of a Lagrangian relaxation method. The optimization may contain nonlinear and non-convex function. Iterative process based on incremental improvement of lambda is required to solve the problem, as we already discussed in the example. But my whiteboard, I select an arbitrary starting lambda, solve the dual problem such that q lambda becomes larger, update lambda using a gradient adjustment. As we already discussed in the example, by taking the partial derivative, we get the value of lambda. Find closeness to the solution by comparing the gap between the primal function and the dual function. Now Lagrangian relaxation for unit commitment. Now for the Lagrangian relaxation for unit commitment, we will first define some variables, because these variables will help us to understand the different iterative table or value of unit commitment. For UI t is equal to 0, if ui over t is equal to 0, if unit I is offline during period t, and when the value of ui over t is equal to 1, if unit I is online during period time t. So now we can define several constraints from the above variables of the unit commitment. These are loading constraint. For loading constraint, this is the equation where t is equal to 1 up to t, and for unit limits, this is the equation. We will get different values and different different functions from these equations. And for unit commitment uptime and downtime constraint, the equation is this one. Formation of the Lagrangian function in a similar way to the economic dispatch. This is the main equation. We will, my colleague will discuss it further in the different tables. From this equation, we can get different values. Unit commitment requires that the minimization of the Lagrangian function subject to all the constraint. The cost function and the unit constraint are each separated over the set units. Here is the one question: what is done with one unit does not affect the cost of running another unit, as far as the cost function, unit limits, and the uptime and downtime constraint are concerned. From my opinion, power system operation planning is very necessary for the best utilization of the available energy resources to meet the varying load demand with maximum safety of equipment. For this reason, very skillful personnel is required, which ensure minimum cost without violating any system constraint. So the Lagrangian relaxation procedure solves the unit commitment by temporarily ignoring the coupling constraint, because other constraint can easily be formulated and added to unit commitment problem, like transmission security constraint, generating fuel constraint, etc. The dual procedure attempt to reach the constraint optimum by maximizing the Lagrangian with respect to the Lagrange multiplier. As we already discussed in the example, how to find the value of lambda, this that was the Lagrangian multiplier. Umayya, this is yours.
Okay, Asim, just stop here. So, Lakshi, can we take break? After that, Umayya may continue.
Yeah, depends on you. If we continue, we will end our class at 3:30.
Okay, Umayya, continue.
Okay.
Asim, off your slide, so Umayya can show.
Okay.
Good afternoon, everyone. My name is Umayya. Do you hear me clear?
Yeah, we can hear you.
Okay. As my colleague said, the Lagrange relaxation procedure solves the unit commitment by temporarily ignoring the coupling constraint. That means we will ignoring the loading constraint, and this done by using the dual optimization approach. Briefly, dual optimization approach means optimization lambda, and then optimization the problem variables, and go back and update lambda. The dual procedure tried to reach the constraint optimum by maximizing the Lagrange with respect to the Lagrange multiplier, and this done by adjusting lambda, and then minimize Lagrange by adjusting the generator value P and U value. So this is my function. We need to maximum Q lambda by adjusting lambda, and we need to minimize Lagrange by adjusting P I of t, Ui of t. Pi of t is output of unit, and Ui of t is a unit. And this done in two steps. Step one, we need to find the value of lambda that make Q lambda move toward at a large value. And in step two, we will assume that the value of lambda that we found in step one is fixed. Then we will find the minimum Lagrange by adjusting the value of P and U. So let's minimize Lagrange. This is a function, this is the equation of Lagrange. Summation t equal 1 to t. Summation I equal 1 to n. Fi, Pi plus startup cost multiply in unit I to t plus summation t equal 1 to t. Lambda t multiply in P load minus summation t equal 1 to n Pi Ui. As we can see, this is a load constraint that what we need to ignore it to solve this problem. So we need to break up this one. So I will do that by multiply the summation lambda t in each one. And we rewrite the equation like this. L equal summation t equal 1 to t, summation t equal 1 to n, Fi Pi t plus Si Ui of t plus summation t equal 1 to t, lambda t, P load minus summation t equal 1 to t, summation I equal 1 to n, lambda t Pi t ut. This Lagrange, this summation over all time, and this summation over all unit, this is rotation cost of the generator, and this is startup cost. This is a unit and have a two state, 0 or 1, 0 for off and 1 for on. And this before a breakup, it's load constraint. Now we will write this equation like this. We will take the two summation as a common mean denominator. So we will write this equation like this. This term is constant since lambda is fixed, so we can't drop it, and we will got in final this equation. If you can note here, now we separate the units from one another, so we can solve this term independently or separately for each unit without regard what happened in another unit. Now to find a minimum of this equation, we need to find the minimum of Q lambda, we need to solve minimum for all we need to solve for all minimum for all unit over all time. And this is subject to unit limitation and uptime and downtime constraint. This is easily solved as a two-state dynamic programming problem of one variable. So as we can see, we have a two-state when generator unit is off and when generator unit is on. At generator unit is off, UI equals 0, and this minimum function is trivial and equals 0. So here equals 0, this all equals 0. And in operating unit, UI equal 1, and the startup costing drop equal drop startup costing and UI equal 1. So we will get minimum Fi Bit plus this lambda t Bit. To find this minimum, this is what I explained in picture. To find this minimum, we need to take the derivative, first derivative of this minimum, and this is so easy. D over dBi to t Fi Pi plus lambda t Pi of t equal d over dBi to t Fi Pi of t plus lambda. Sorry, this is a minus, not plus. Here, this is minus, not plus, okay? So we will take this lambda to another side, and final, we will get d. The first derivative of Fi Bi of t equal lambda t. And this is concerned for P, and there is a 3 cases to be concerned for Bi of optim and unit limitation. So case 1, if Pi opt less than or equal Bi mini, then here we will put Pi mini, like this here. And if Pi opt more than or equal Pi mini, less than and equal or equal Pi max, here we will put Pi optim. The last case, if Pi max less than or equal Pi opt, then the mini will put here in mini Pi max. As summary, the two-state dynamic problem is solved to minimize the cost of each unit. Okay, and as we said, when UI of t equals 0, the minimization is travel and equal 0. So we have a only way to have a lower cost is to have this less than 0. Now we will adjusting lambda. Okay. We have shown how to schedule generating unit with fixed lambda t for each time period. Now we will adjusting lambda. The adjusting lambda must be done careful so as to maximize Q lambda. The Lagrange relaxation procedure use a combination of gradient search and various heuristic to get a rapid solution. So this is a gradient component where this is a heuristic component. The gradient component lambda of t equal lambda t plus the first derivative of q lambda alpha. Alpha is constant and have 2 values. When the first derivative of q lambda is positive, alpha equal 0.01, and when the derivative of lambda the derivative of q lambda negative alpha equal 0.02. The last topic I will talking about the relative duality gap. The relative duality gap uses as a measure of the closeness to the solution. So we will use it to see the closeness to the solution. For a large size power system unit commitment calculation, the duality gap becomes quite small as a dual optimization procedure. That means when the large commitment there is a lot of unit, that means the gap is so smaller. The configurance is unstable at the end. So the units are being switching in, on, and out, and the process never comes to define end. There is no guarantee that when the solution process stop, it will be at the visible solution. The gap equation, this is the gap equation. So now, Asim, it's your time, it's your turn. Any question? Hello?
Asim had given Umia its turn for herself.
Okay, let me.
Umia, kindly end your share so I can share my slides.
Okay, if anyone has a question regarding Umia, so he may ask.
You have any question?
Okay, so continue.
Okay, continue.
So we will see an example for Lagrange relaxation algorithm using dual optimization. And this is the algorithm how to solve the problem. First, we start and pick the starting value of lambda t, and t is equal to 1 to t, how many hours you have, and start the constraint at 0. Start for the iteration for 1 and see for every unit, do the loop. We will see this better explained version. Build a dynamic programming. Dynamic program is something like which has multi-stages. We can choose 2 units, 3 units at the same time, not only 1 unit. So we can choose how many units we want to run at the same time, and we can build a system, build a plan that depend upon the dynamic programs. So until the last unit is done. If not done, then we go back and do for the every unit. When all the units are done, then we solve for dual value Q star, which after that we go to calculate the primal value J prime, and it is also solve the economical dispatch for each hour using the units that have been committed for that hour. Then we calculate the relative duality gap, which will show how much we are close to our solution, to our having the cheap output. And if the gap is minimum, something around 0.05, then we can move toward final solution. And if the gap is high, then we need to go back and do the calculations again, and we need to transform our lambda values again, so we can have our optimum values of our duality gap. After this, we have an example. We will see how solve the railgate scenario during by the Lagrange relaxation algorithm using dual optimization. So this is a problem which has 3 generator system, and it is running for 4 hours, and we have to assume that there is no startup cost and no minimum uptime or downtime. And it is a plot which is during first hour it is 170 megawatt, second hour it is 520 megawatt, third hour it is 1100 megawatt, fourth hour it is 330 megawatt. And this is the cost of the generations. By using these, we can see we'll do calculations in our further process. So we will start by taking all the lambda t values to 0, and as we said that when the system is minimum value, we can take the cost up to 10,000, 10,000, and the j value can be summed up all the units. Then we can have the j prime value. So at the first iteration, we have all the units equal to 0, all 4 hours, 0, 0, no one is running. So our lambda value is also 0, starting value is 0, and our j prime value is summed up as 10,000, 10,000, 10,000, 40,000 equal. And as the q is 0 at the start, so our duality gap is undefined in first iteration. Moving toward our second iteration, second iteration we have our unit 3 working on at third hour, and it is at 1100 megawatt, because our third hour our load is 1100 megawatt. So according to this, we need to calculate our lambda values, and we need to calculate these. We will see how to calculate that. First, we need to adjust our lambda values. So it is the equation that Umia already told. The lambda k plus 1 is equal to lambda k plus partial derivative of q multiplied by alpha. So our alpha is 0.01, as I already told. It is alpha will be, it is this equation. Alpha will be 0.01 when the slope is positive, and the alpha is 0.002 when the slope is negative. So by using this equation, we are transforming our lambda t into new lambda t's. So the alpha is 0.01 and the q is positive. So our iteration number 2, t is equal to 1, first hour. Our lambda 2 is equal to lambda 1 plus derivative of multiplied by lambda. So first hour 1.7. According to the same procedure, we also take our lambda 2 is equal to 5.2 and lambda 3 is equal to 11, and lambda 2 at fourth hour is equal to 3.3. So moving forward with this, we put these values of lambda here. Lambda 1 is equal to 1.7, lambda 2 is equal to 5.2, lambda 3 is equal to 11, and 3.3. So these are the values, and now we need to calculate these values. These values we have already calculated here. This is the third iteration for lambda 3, that is for next stage, and this is the calculation of cos minus lambda p for unit number 3, because at first our second iteration our unit number 3 is running. So at t f3p is equal to 100 plus, it is from the equation here, from these equations I take the values. So here 100 plus 6 f 6 p3 plus 0.005 p3 2. So as the p3 we have between the 50 and 200, it is already given in the problem. So when the minimum value, when the one station is small, like it is already given values that power of the third unit is between 200 and 50. So when it is off, then we can take it as a 50 minimum value. So the transforming is the calculation is fp minus lambda p, 100 plus 650, as the 50 is equal to p3 and p3 is equal to minimum value. As it is off, it is 50, and we get the calculation and equal to 3 to 7.5. At second hour, we take lambda is equal to 5.2 as already calculated, and we calculate these things, and it is 152.5, and at 3 it is minus 700, and it is 4, it is 247.5. So these calculation all already done. So moving forward with the third iteration, we use our two generations. Like at first hour, we not use any of our units. At second, we use our 2 units. At third hour, we use our 3 units. So we need to calculate these again. First, we need to calculate our lambdas. Then we need to calculate our q of lambda. Then j prime. Then our duality gap. This is our iteration 4 of lambda, which I already explained you how to calculate. So we can calculate the updated value by previous value plus gradient multiplied by alpha. It is very simple, but here we need to calculate our q value. here it is 300 for second iteration when the third unit is running. 300 plus 100 multiplied by 2 multiplied by 400 plus alpha plus 400 square. It is the same equations that already given in the problem. So we take these from there and do calculation for third iteration, and for fourth iteration it is updated, and J omega and duality gap. Need a calculation here. Here is our duality gap. We take the values calculated for Q of lambda and J of lambda, and we take the differences for different iterations, and we see, and same procedure we apply and check the duality gap. We need duality gap very low until 0.00, until about 0.05 is okay. Full zero we very rarely have. So at 4, 3, 4, 5, 6 iterations, we are having lower and lower, something like 0.9, then 0.5, then 0.8 again. So it is oscillating, and we get it at 6, 0.03, and at 0.03 it is quite small. So we can stop our solution here when the duality gap is less than 0.05. So here we stop it, and I will explain the ending. It is the ending here. We should stop at the iteration number 6. The frequency rule does not change significantly with the further iteration. With the further iteration, it is not decreasing very much, and it is already small enough, so we can stop our iterations. Although it is not by any means stable, because it is not stable, it is going to 0.9, then 0.5, then 0.3. So it is not much stable. Further iteration do reduce the duality gap somewhat, a little bit, but these iterations are unstable in that unit 2 is on the borderline between being committed and not being committed, and it is switched in or out with the no final convergence. After 10 iterations, the Q lambda value is equal to 19,485, J prime is equal to 20,017, and our duality gap is 0.027. This later value will not go to 0, and nor will solution settle down to a final value. Therefore, the algorithm must be stopped when the J prime minus our duality gap is significantly small, and 0.05 is small enough, so we can stop our solution at 6, or maybe at iteration number 10. So after here we can have our uh, optimum condition how to run our system, so we can have reliable and cheap output of the systems. Our problem ends here, and Kazi will do the endings.
Okay,
Any
thank you, Asad.
question, then you can ask me.
So in your group, there are okay. Oh, that's bad. Okay.
So anyone have question related to our topic 7, you may ask. Or if you want to give any suggestion that what we have to improve in our presentation.
Yes, I want to give some comments for your presentation. I think your group do a wonderful job. I think actually this part is a very difficult part, especially for the Lagrange function. I think you give a very presentation, and thank you so much.
Okay, Lakshi, thanks so much. If any, I send my solution, Asad will send in group. So if anyone have question regarding this problem, we will help them. Thank you.
Okay, so in your group, there are only 4 members, yes?
Yeah, Lakshi, I have told that private that had left this year.
Okay, okay.
She is finished this year.
Okay.
Next year.
I just make sure that there's no mistake. Okay.
Okay. So any other question
Thank you,
you
sir.
may ask. So we may end this presentation.
Okay.
If anyone want a video, he may send me a message. I will send him personally.
Okay, okay. Thank you so much.
Thank you.
Okay, so if we don't have any question, we will end our class now. Okay.
Thanks so much.
Okay. Thank you all. Thank you for coming to hear this presentation. Thank you all.
Thank you. Thank you.
So many thanks for your comments. Thank you, sir.
Bye bye. Thank you.